Meta sections. WM. Copyright statement. This 172.4.1 contents. Stress analysis. Used to determine the loading of the body. If the body is in equilibrium, any part of the body is in equilibrium. Define forces with numbers. Imaginary sections used to determine and exposed internal forces external. The meta sections. Stress analysis. Point 3 form simply support just within point G and roller point E. Loads P1, P2, and P. When the force is known, the number of forces of the very few number desired, the meta section works well. To determine the force number BD, form section I. Cutting through stress and create a free body diagram to the left side. And FBD given created to the right side. Why is this less desirable choice? Think and discuss. Point 3 form simply support just within point G and roller point E. Loads P. Stress analysis. Point 3 form simply support just with the sections created by making a vertical vector number GD, P, and C. The number forces FBD, FE, and FC. Notice that the exposed internal forces are all assumed to be in tension. Cut KK is for numbers GD, P, BC, and AC. Cut PP is for numbers. Notice that anything can be chosen so long as it creates a separated section. So, for example, this step with line PP is acceptable. Stress analysis. Meta sections. Stress is made of several simple stresses. ABC is the stress in the shape of a triangle. Point at the bottom left and point C. ABC is this stress contains a number and is therefore statically indeterminate, making m greater than 2 n minus 3. Stress is made of several simple stresses. ABC is the stress in the shape. ABC is rigid. M plus 4 equals 2 n. Additional reaction forces may be necessary to make the stress rigid. Necessary to the condition for compound stress to be statically determinate, rigid, and completely constrained. M plus r equals 2 n. Point 3 form simply support just within point A and roller. Point 3 form simply support just within point A. 1. Draw the FBD for the entire stress. Apply equilibrium conditions to solve the reaction to A and L. 2. Make the numbers of H, GH, and GI and take right hand sections. Free body left side would also be acceptable. 3. Apply the conditions for static equilibrium to determine the desired number of forces. Free body diagram of stress. Free body diagram using section N. Number of forces at FH, FGH, and FGI are exposed. What is the one equilibrium equation that can be solved to find FGI? Confirm your answer with the neighbor. Sum of the moments at point H. Kappa sub kappa kappa equals 13.13 kilonewtons kappa T. FGGG equals 13. Kappa sub kappa kappa equals 13.81 kilonewtons kappa. FFH equals 13.8. There are many options for finding FGH to this point. Here's one more. Kappa sub kappa kappa equals 1.371 kilonewtons kappa T. FGGH equals 1.371 kilonewtons cc. Sample problem 1. Reflect and think. Sometimes teachers resolve forces and components included in equilibrium equations. By first sliding this force along its line of action to a more strategic point, you may eliminate one of its components from an equilibrium equation. 17. Office faculty department. The method of choice is usually the best method to use when you need to find the forces in all the members of a simple press. The method of sections is more efficient when you need to find the forces in all the number of forces in a very few members of a simple press. The method of sections also must be used when the stress is not a simple press. To determine the force in a given stress number by method of sections. 1. Draw a free body diagram of the entire press and determine reactions to the supports. 2. Pass the section through 3 members only. Of the press, one of which is the number whose force you want to find. 3. Select one of these two portions of the press and draw a free body diagram. 4. You can now write three equilibrium equations that can be solved for forces in the three intersecting numbers. There are special cases where you can come up with three members. You can make equations that solve directly from in this video, we are going to introduce another method for simple cross analysis of method of sections. Once again, for any cross number that is either intentional or compression, if we want an imaginary structure to it, the internal force can be imagined to have been exposed and can be considered as external. So now we have a way to apply free body equilibrium method to analyze internal reaction. We will learn more about the internal reactions later. Since if you recall, one 3D free body diagram enables us to solve for a maximum of 3 unknowns. So if we only need to solve for the forces in no more than 3 cross members in the structure, we can imaginarily cut the structure open and apply free body equilibrium analysis. This is known as the method of sections. Let's look at an example. For this structure, we are not asked to solve for all members, just BC, CF, and CG. Therefore, instead of using the method of points, we use the method of sections because this is the way there are fewer steps involved. Here's the plan. Since we need to solve for the forces in numbers BC, CF, and CG, we can run an imaginary cut through these three members. And now the internal forces in these three members are exposed. Note how there are actions and reactions on the left and right segment. So we can choose either side for calculation and we will get the same results. Don't forget, we can only solve for 3 unknowns using one rigid body equilibrium diagram. Therefore, either side we choose, we need to determine the support reaction first. Now, the left segment has only one support reaction associated with the rotor, while the right segment has two support reactions associated with the thing. So for the means, we pick the left segment for further analysis. So for the first step for this problem, it is necessary to determine the support reaction at point A. To do so, we draw the free body diagram for the entire structure and summarize the result in a moment about point D. And from this single equation, we are able to solve for the force AY. Keep in mind that for some problems, it might not be necessary to determine the support reaction, so you should use your own judgment. Step 2, cut the structure, and we have already decided to choose the left segment for our analysis. Step 3, apply free body equilibrium to solve for our unknowns. We start with a free diagram of the left segment, and since we have already solved for the support reaction at point A, we have only 3 unknowns, FBC, FCF, and FFG, and we write 3 equilibrium equations. Remember, normally we would write 2 force equations and 1 moment equation. However, note that how force BC and force CF are concurrent, and force CF and force FG are also concurrent. Therefore, it would be convenient to write 2 moment equilibrium equations about point C and point F. See, when the moment is summarized about point F, only FBC shows up and can solve easily from this equation. And when the moment is summarized about point C, we only have force FG and can easily solve it as well. Lastly, let's write one force equilibrium equation along the x direction, and finally we can solve for FCF. Hopefully, from this example, we have learned how to apply method of sections for reciprocal cross analysis. We actually have already learned a little bit about the internal forces when we studied the reciprocal cross analysis. For a cross member with forces acting on it, the member could be in tension or compression. And although the forces only act on the two ends, force must also develop inside the member because we should be able to run an imaginary cut at any place within the member. And each segment must also be in force equilibrium according to Newton's first law. These forces are internal forces. They are exerted by the materials to keep the segments on volume. This is a very simple example of internal forces, and we are about to learn more complicated cases. But before doing that, let's take a moment and think why we are interested in learning about internal forces. You probably come to this answer. We want to know the internal force so we can make sure it does not exceed what the material can withstand. We don't want the members to fail on the doings. Actually, it is not the force that matters because we have simply use a thicker, bigger member, and that seems to fix the problem. It is the force over the area, stress, that cannot exceed a certain value. The stress associated with internal moment force that the one seen across the members is normal stress, sigma, which is calculated as F over the cross area of the member A, and it should not be greater than an allowable value. As you can probably tell, this is beyond the current statics class, but it is always good to know why we're learning what we learn. Now let's look at a more general example. In this example, we have a level point A is a fixed support, and we're asked to find the internal forces at point B. Since we're asked to solve for internal forces, we need to first expose those forces, become external, and then we can draw the free body diagram and apply free body equilibrium analysis that we already learned. In fact, we are not familiar with this approach since we used it to solve for truss forces already, and this method is called the method of sections. Now let's look at the proper procedures when applying the method of sections. First step, determine the maximum support reactions and complete the free body diagram of the entire member if necessary. Of course, sometimes it is not necessary to do so, and you will be able to afterwards. But for now, let's just solve them. Since at point A we have a fixed support, there are 3 support reactions, 2 forces, and a moment, and we can solve for all of them by applying free body equilibrium analysis. Step 2, cut the member at a specified point, and in this case point P. And we separate the two parts. And now we need to specify what kinds of unknown reactions we should draw at the cut. Let's look at the right segment. It is being held by the left segment, and it is not allowed to move horizontally or vertically or rotate. That sounds just like a fixed support. In fact, don't forget in this class, we assume all members that we study are non-deformable. Therefore, any portion of any member can be considered to be held by an imaginary fixed support. So let's draw the same unknown reactions as the fixed support. 2 force reactions and 1 unknown reaction. And because of actions and reactions, we can also draw the unknown reactions on the left segment. They have the same magnitude for opposite directions as the ones on the right. And therefore, we only need to solve for one set of unknown reactions, either from the left segment or from the right segment. So step 3 is to choose one side and solve for unknowns. I will demonstrate calculations using both sides just to show that they will lead to the same answers. But when you make your own pick, of course you want to choose the side that makes calculation easier. In this case, you should pick the right side so you don't need to solve for the support reactions in the first place. So with the left segment in our appropriate coordinate system, write the 3 two-dimensional rigid body equilibrium equations. Force along x direction, force along y direction, and set the moment about point B. And we can solve for all 3 unknowns. And we can do the same thing for the right segment and get exactly the same answers. Note that we want to summarize the total moment about point B because this way the unknowns BD and MB would not cause any moment about point B, therefore they do not show up in your moment equilibrium equation. Now, let's look at these names. The first one is normal force because it is normal or perpendicular to the cross section of the member. We already familiar with this one because all forces we solve for reciprocal analysis are normal forces. The second one, V, is shear force, and it is always tangent to the cross section. The third one is the bending moment, and as you can tell, it causes a bending tendency in the member. Although we can define the positive directions of these internal forces whichever we want, there are a set of sign measures. The purpose is for better communication between engineers, so other engineers can quickly interpret these calculations. According to the sign measures, for a 2D problem, the normal force is considered to be positive if it's tensile. The shear force is considered to be positive if it creates a clockwise rotation impact on the segment. And the bending moment is considered to be positive if it creates a concave upwards bending impact on the segment. I would suggest you always draw your own internal forces according to the sign measure to avoid confusion. Now let's quickly look at another example. Determining the internal forces at point C. Again, we are going to apply the method of sections. First, let's choose the side we want to solve. In this example, we inevitably have to solve for some external support reactions first. But at point A we have a roller support which only has one support reaction versus at point B we have a support with 2 support reactions. Therefore, we choose the left side with the roller support. So we solve for force FA at the roller support using one moment equilibrium equation. And now we run an imaginary cut through point C and analyze the left segment. We draw the 3 internal forces according to the sign convention: the normal force, the shear force, and the bending moment. We need to replace the distributed load by an equivalent concentrated load. Now we set up the rigid body equations and we can solve for all 3 unknowns. What if we have a 3-dimensional problem? For example, for this beam that is tangent to the axis of forces shown, what are the internal forces at point C in this beam? Well, we can solve the problem using the same method of sections, following the same procedures as described for the 2D problems. We run an imaginary cut through point C, separate the two parts, pick one side to solve, determine the support external reactions necessary, put the segment in an appropriate coordinate system, draw the unknown internal reactions the same way for a fixed support, and solve for all unknowns by applying 3 dimensional rigid body equations. Keep in mind that for 3D problems, there are no sign conventions like the ones we have for 2D problems. Therefore, the signs for the internal reactions will depend on how you set up your coordinate system. Let's say we choose the left segment, and these are the 6 internal reactions, and we can solve all of them by applying the 6 rigid body equations. Now we have one normal force that is on the axis direction, and it's perpendicular to the cross section. You have 2 shear forces that are tangent to the cross section, 2 bending moments, and also you have 1 torsional moment that creates a twisting effect on the member. As you will learn in the class on mechanics of materials, these different internal forces will cause different types of stresses and deformations and even failures in the members. In the previous video, we learned how to determine the internal forces that specify the location of a member. However, we would want to know where the maximum internal reaction happens in the member because that's where the member is most likely to fail. And in most cases, we cannot use a type of we actually have already learned a little bit about the internal forces when we studied the simple force analysis. For a trust member with forces acting on it, the member could be in tension or compression. And although the forces only act on the two ends, Frames Machines, WMEC, copyright, contents, application, https://application, https://Charlie Mann on top machinery, maximum rate, no field versions before Bob developer. Introduction, A, trusses, form 2 force members, i.e. string members with connections and forces acting on these endpoints. Introduction, B frames, contain at least one multi-force member, i.e. member acted on by three or more forces. Introduction, analysis of the frame. A free body diagram with complete frames used to determine the external forces acting on the frame. Internal forces are determined by determining the frame and creating free body diagram for each component. Analysis of the frame. Forces on multiple force members have a non-negative line of action. They must be represented with two unknown components. Forces between negative components are equal, have the same line of action and opposite sense. Frames that collapse without supports. The frame supported by pinpoints A and B. Vertical is P and Q are applied members AC and DC. The frame supported by pinpoints A and B. Vertical is P and Q are applied members AC and DC. Point B is the right point A. A free body diagram with complete frame indicates four unknown force components which cannot be completely determined from the three available equilibrium conditions for the SPD. Free body diagram of the frame. The frame must be considered two distinct, related rigid bodies. Frames that collapse without supports. Equilibrium requirements for the two rigid bodies yield six independent equations. Thus, taking the frame apart makes the problem solvable. Free body diagram of the frame. The frame supported by pinpoint A and lower point B. A480 Newton. Numbers AC and DC are connected by pinpoint C and by Lambda. For the loading shown, determine the force and the components of the forces of the C on number BCD. The frame supported by pinpoint A and lower point B. A480 strategy. Follow the general procedure discussed in this section. First, treat the entire frame as a free body, which will enable you to find reaction to A and B. Then dismember the frame into each member of the free body, which will give you the equations needed to find the force C. Free body diagram of the frame. Modeling analysis. Create a free body diagram with complete frame solve the support reactions. Free body diagram of the frame. A y cap equals 300 and B equals 300, cap x equals 300 and left arrow. AXX equals 300 and left point arrow. Note, top figure. Free body diagram of the frame. Create a free body diagram of member BCD since the problem asks for forces on the body. Choose the best FPD, then set your choice to the neighbor. Justify your choice. Top figure. Free body diagram of the frame. Middle right figure. Free body diagram of member BCD. Bottom left figure. Free body diagram of member BCD. Bottom right figure. Free body diagram of member BCD. A, B, C, D. Free body diagram of member BCD. Using the best FPD for member BCD. What is the one equilibrium equation that can be used directly to determine FE? Please discuss. Free body diagram of member BCD. Using the best FPD for member BCD. What is the one equilibrium equation that can be used directly to determine FE? Please discuss. Free body diagram of member BCD. FFPD equals 561 and CC. Sum of forces in the x and y direction may be used to find the force components at C. Cap C sub x equals minus 795 n. CCx equals minus 795 n. Cap C sub y. Free body diagram of member A and D. Reflect and think. Check the computations by considering free body A's. Checks. Machines. An input force to be applied to the handles and the output force to keep the wire and adjust the pliers. An input force to be applied to the handles and the output force to keep the wire and adjust the pliers. Given the magnitude of P, determine the magnitude of Q. An input force to be applied to the handles and the output force to keep the reaction against adjust the pliers. Create a free body diagram of the complete machine, including reaction to the wire exerts. The machine is a limited structure. Use one of the pieces of free body to specify the forces that are such as shown. Some moments about A. Summary. Equilibrium equations apply to 1. Entire body. 2. Joints and method of joints. 3. Section method of sections. 4. Members of frames machines. 5. Pieces of members to internal forces. Internal forces in many moments. WMEC, WCI, UNO, copyright, this material, contents, application, introduction, internal forces and numbers, internal forces and numbers, internal forces and numbers, crane made up of vertical number ABCD, horizontal number CF, and diagonal number B, crane supported by pinpoint A and D, lower point, crane made up internal forces and numbers, shear forces in many moments, the frame supported by pinpoint A and lower point F, determine the internal forces, A, number AC at the point J and B, and number BCD at K. The frame supported by pinpoint A and lower point F, strategy, compute reaction to forces and connections for each member, cut number AC at the J, the internal forces at J represented by equivalent force systems determined by considering equilibrium, cut number BCD at K, determine the force systems equivalent to internal forces at K by finding equilibrium conditions to apart. Modeling, compute reactions and connection forces, analysis, consider entire frames of free body, and apply equilibrium conditions. FFY equals 0 equals minus 2 4 and FFF equals 1 8 FFFY, free body diagram of member BCD, dash, y forces of B and C drawn in these directions, is there a choice on directions, y there are two force components each point instead of just a single force. Think about these in discuss. Drawing the FPD for member. BCD, drawing the FPD for member. A, y forces of B in these directions, is there a choice on directions, y there are two force components instead of just a single force. Think about these in discuss. Finally, the FPD for member. ACF, sample problem 7.1, free body diagram of member BCD, consider member BCD as a free body, MMCC equals 0 equals minus. Sum of cap sub cap C equals 0 equals minus open 2 4 close random 1 point meters, close rand plus cap C sub y, open 2 point meters, close rand. FFX equals 0 equals minus BDXX plus CCX equals 0 y, delaware BDXX equals CCXX. Sample problem 7.1, consider member A as a free body. Any information that FX equals 0 equals BDXX minus AXX equals 0 y, from member BCD, free body diagram of the portion J and F J member ACF. Cut number ACF to J, the internal forces at J represented by an equivalent force system. Consider free body AJ, free body diagram of the portion J and F J member ACF, M equals 2100, cap equals 1340, F equals cap equals 1197 n. VB equals 11, free body diagram of the portion DK and DK member, cut number BCD at K, determine the force system equivalent to internal forces at K. Consider free body DK, cap equals minus 180 and that M equals minus 180 and that operator M. Free body diagram of the portion DK and DK member BCD, cap VB equals minus 1200 n. Reflect and think. Reflect and think. The mathematical techniques involved in solving the problem of this type are not new. They have simply applications of concepts presented in earlier chapters. However, the physical interpretation is new. We are now determining internal forces and moments in a structural number. These are central importance in the study of mechanical materials. The mathematical techniques involved in solving the problem of static friction. WMEC, WCI, UNO 1, week 6 plus 1, copyright, this material, contents, application, the laws of direct friction, coefficients of friction division, further increase in P because of the block begin to move, while the drops to small kinetic friction force FF. KK, dot, FF, KK, equals, MKK, NN, M, bold calc sub, bold calc bold calc and subscript. Maximum static friction force and kinetic friction force are proportional to normal force, dependent on type and condition of contact surfaces, independent of contact area, metal on metal, 0.15 minus 0.60, metal on wood, 0.0 minus 0.60, metal on stone, 0.30 minus 0.70, metal on 0, wood on leather, 0, rubber, 0, kinetic friction force, FF, KK, equals, MKK, NN. No friction, PS equals 0. Block with weight W, position on horizontal surface subject to force T, acting down. No friction, N equals P plus W, PS equals 0. Block with weight W, position on horizontal surface subject to force T, acting down to the right. No motion, PS less than F, F equals PX, F less than micro, N equals P y plus W. No motion, PS less than F. Block with weight W, position on horizontal surface subject to force T, acting down. No friction, N equals P plus W, PS equals 0. Motion depending PS equals FM. Block with weight W, position on horizontal surface subject to force T, acting down to the right. No motion, PS less than F, F equals PX, F less than micro, N equals P y plus W. Motion, PS greater than FM, or motion while recurring. The laws of right friction, angles of friction. Block with weight W, position on horizontal surface subject to force T, acting down. No friction, R equals N. Block with weight W, position on horizontal surface subject to force T, acting down to the right. No motion, F equals PX, phi less than phi S, reaction or acting down to the left. No motion, block with weight W, position on horizontal surface subject to force T, acting down. No friction, R equals N. Motion depending. Block with weight W, position on horizontal surface subject to force T, acting down to the right. No motion, F equals PX, phi less than phi S, reaction or acting down to the left. Motion, the laws of right friction, angles of friction. Block with weight W, position on horizontal surface. No friction, theta equals 0. Block with weight W, position on inclined surface. No motion, phi less than phi S, N equals W plus theta, F equals W plus theta. No motion, block with weight W, position on horizontal surface. No friction, theta equals 0. Motion depending. Block with weight W, position on inclined surface. No motion, phi less than phi S, N equals W plus theta, F equals W plus theta. Motion, problems involving right friction. All applied forces known. Motion is depending. Determine value of coefficient of static friction. 300 pound block is position on incline with a slope of 3/4. 100 pound force acting on the plane is applied to the block. N. 300 pound block is position on incline with a slope of 3/4. 100 pound force acting on the plane is applied to the block. N. 300 pound block is position on incline with a slope of 3/4. 100 pound force acting on the plane is applied to the block. Strategy. Draw the free body diagram for the block. Remember that the friction force is opposite direction of bending motion. Determine values of friction force and normal reaction force and plane required to maintain equilibrium. Calculate maximum friction force and compare friction force required for equilibrium. It is greater. Block will not slide. If maximum friction force is less than friction force required for equilibrium, block will slide. Calculate kinetic friction force. 300 pound block is position on incline with a slope of 3/4. 100 pound force acting on the plane is applied to the block. N. N. Free body diagram showing apply 100 pound weight force, normal force, friction force acting on the plane. What is the sign value about the assumed direction of bending motion? Think about this and discuss with the neighbor. Free body diagram showing apply 100 pound weight force, normal force, friction force acting on the plane. N. N. What is the solution applied by the block? Discuss this with the neighbor. Free body diagram showing apply 100 pound weight force, normal force, friction force acting on the plane. N. N. What is the solution applied by the block? Discuss this with the neighbor. The block will slide down the plane. Free body diagram showing apply 100 pound weight force, normal N. N. Free body diagram showing apply 100 factual equals 48 N. Free body diagram showing apply 100 pound weight force, normal force, friction force equals 48 pounds acting on the plane. N. 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 Sample problem 8.1. Reflect and think. This is a typical friction problem of the first type. Note that you use the coefficient of static friction to determine the degree of moves, but once you found that does move, you need the coefficient of kinetic friction to determine the friction force. 17. Office faculty department. The bracket slides on two 3-inch diameter collars. One at the top of the bracket and one at the bottom. The logo W, acting now, is applied to the bracket distance x center of the pipe. CM. The bracket slides on two 3-inch diameter collars. One at the top of the bracket and one at the bottom. The logo W, acting now, is applied to the bracket distance x center of the pipe. CM. Draw free body diagram of the body under steady bracket. Apply conditions for static equilibrium, find the max. The bracket slides on two 3-inch diameter collars. One at the top of the bracket and one at the bottom. The logo W, acting now, is applied to the bracket distance x center of the pipe. CM. CM. Free body diagram bracket. FA and R applied to point A. CM. CM. Free body diagram bracket. FA and R applied to point A. F flat applied to point B. The force W is applied 1.5 inches per center of the collar. CM. CM. NNB equals naught. NNA equals NNB equals CWW. X equals 12 centimeters. Rectangle. X equals 12 centimeters. Note that it doesn't matter what W is. Does this make sense? Free body diagram bracket. FA and R applied to point A. F flat applied to point B. The force W is applied 1.5 inches per center of the collar. CM. 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 Sample problem 8.3. Reflect and think. In a problem like this, you may not figure out how to solution until you draw the free body diagram and examine what information you're given when you need to find. In this case, since you were asked to find the distance, the need to evaluate moment equilibrium should be clear. 22. Office faculty department. Wedges. Free body diagram of wedges. 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 Free body diagram of block showing the weight force W. Friction and normal forces from the wall. F1 and N1 as well as friction and normal forces from the weight C. F2 and N2. Wedges. Free body diagram of weight C showing friction and normal forces from block A. F2 and N2. Friction and normal forces from the weight D. F3 and N3 as well as force P. Square threaded screws. A block is positioned on an inclined plane. Force Q is applied to the block. The weight force W is shown. The reaction from the plane R acts on the left. Moment of force Q equals moment of force P. Q equals R. A block is positioned on an inclined plane. Force Q is applied to the block. The weight force W is shown. The reaction from the plane R acts on the right angle phi S left vertical. Phi S greater than theta. Self-locking, self-repeated low load. A block is positioned on an inclined plane. Force Q is applied to the block. The weight force W is shown. The reaction from the plane R acts on the left. Phi S greater than theta. Non-locking, self-repeated low load. Using the blocking plane now, do the motion of the plane. Calculate the time force of the force triangle. Reflecting the motion down the plane. Calculate the force and calculate required to loosen the clamp. Free body diagram of the block. Force triangle forces W, Q and R. Tan. Force triangle forces W, Q and R. Capital W equals 17.97 kilonewtons. Rectangle. Free body diagram of the block. Q equals 2.975 kilonewtons. Sample problem 8.6. Reflect and think. In practice, you often have to determine the force effectively acting on the screw by setting the moment that force of the axis of the screw equals to implied couple. However, the rest of the analysis is mostly an application of dry friction. Also note that the couple required to loosen screw is not the same as the couple required to tighten it. 32. Office faculty department.
If you're currently aware. Welcome to the lecture line. One of the practical applications of the concept of a wedge is one of the screws. In this case, we're going to call a square threaded screw. What we're trying to do is we try to turn it counterclockwise so that the screw will come out. So we have any motion upward. And the way we look at it is that the screw will have a certain amount of weight pushing down. That could be because there's pulling something down, so using the weight of the screw. We're going to push against the electric into the angle and distance r away from the center of the screw. So this is the moment arm, this is the force applied Fp, such that the force applied to the thread itself can be found by taking F of P and multiplying times the ratio of the moment arm of the applied force divided by the radius of the screw itself, the mean radius of where the thread touches the object which is the screw. So you can see that large r is much larger than small r, so the force applied to the screw is very large due to the moment arm right here. So when we take a look at what happens at the thread itself, we can imagine this being the thread of the screw pushing against the object, which of course also is threaded. And so if we're pushing against the screw so that the screw will line itself upward, we can see that the thread of the screw will be pushing against the thread of the object that's embedded in. So the reaction rate force will go this way, which is the sum of the normal force plus the friction force. And again, if you know the coefficient of friction, in this case, it's nothing moving, we're talking about pending motion upward. We take static coefficient of friction, and the angle phi is equal to the arctangent of the static coefficient of friction, such that the angle of the reaction rate force and the vertical will be the sum of the angle made by the thread, which is called the weak angle, and the angle phi, which is caused by the coefficient of friction. We must add those angles together. Notice that this here represents the distance of one complete rotation of the thread, which is 2 pi times r, small r being the radius, mean radius of the thread. So this is imagined to be the entire distance of the one time around the screw, so to speak. And so then you can see that the thread will work its way up, or the screw will work its way up the thread. That's how you want to take a look at it. So we have the weight of the screw, the force applied to make the screw go upward, which is caused by the force here on the angle, and then we have the reaction rate force. Now when we take those three forces together, since nothing's moving yet, we're pending motion upward, we can add the three forces together and triangle like that, therefore they must add to 0. So we have the weight of the screw, the force applied to the moment of the force here, the moment applied to the screw, and then we have the reaction rate force of the thread. And notice that the angle between the weight, which is vertical, and the reaction force is simply the lead angle plus the angle caused by the friction between the surface and the screw. And that's what we want to think about the general concept of the threaded screw, which is very similar to the concept of the wedge. And so that's where that's coming from. That's how it's done. Welcome to the lecture line. Here's another typical example of a wedge problem. What we're trying to do here is drive a wedge into a log, trying to split the log. And the question is, if we're applying a force of 720 pounds down the wedge, which has an angle of 12 degrees, what will be the force against the wedge in the horizontal direction? We know that the coefficient of static friction between the wedge and the wood is 0.3, which allows us to find the angle phi, which is the angle between the reaction force and the normal to the wedge. We can say that phi will be equal to the arctangent of the static friction. And the calculator we can find out what that's equal to. So 16.7 degrees. Phi equals 16.7 degrees, which now when we do a summation of the forces involved, we have a 720 pound force pushing down, we have two reaction forces in this direction. And notice if we add 16.7 degrees to 6 degrees, which is half of 12 degrees, which is the angle between the horizontal and normal, we have an angle here together of 22.7 degrees, which allows us now to draw the sum of the three forces. We have the, let's put it over here. So we have the force driving down the wedge, we'll call that W, which is 720 pounds. It's synonymous with the weight of the object, in this case the force driving the wedge. We have reaction force 1 coming this way, and reaction force 2 coming this way. Of course, the forces together should add up to 0. So this is reaction force R2, this is reaction force R1. And we also realize that if we divide this in half, we got this into a sum of two right triangles, that here the horizontal line here represents the force pushing against one side. So that's what we're looking for. We're going to put this F right here. So what we need to do is we find this angle, which is the angle horizontal relative to the reaction force, which is this angle right here. Notice this angle is 22.7 degrees. Here's the full force of the full magnitude of the force applied to the wedge. We take half of that. We have a force of 360 pounds. And then we have this angle of 22.7 degrees, which allows us to find F, because now we have a relationship between the distance side, the opposite side, and the angle. We can now say that the tangent of 22.7 degrees is equal to the ratio of the opposite side divided by the distance side. In this case, the opposite side is half of the force applied to the wedge, 360 pounds, and the distance side would be F, which is what we're looking for. And that allows us to solve for the force. And we can say that F is equal to 360 pounds divided by the tangent of 22.7 degrees. 360 divided by 22.7, take the tangent of that, and we have a force of 861 pounds. So F equals 861 pounds. So now you can see that by driving a wedge into a piece of wood like this, trying to split it, we apply this force right here based upon the coefficient of friction, and it's the angle of the wedge. We apply 4 forces horizontally against the wedge, splitting apart of 861 pounds to the right, the force is equal, and opposite force to the left is 861 pounds to the left. That's how it's done.
Distributed forces, center of mass, center of gravity, and centroids. WMEC 101 week 6 copyright statement. 172.4.191.17 megabytes. Contents. Center of mass. Application. Center of mass CM. CM is a point around which mass and object is equally distributed. Can you get the CM of the following distributed objects? Assume that the mass is uniformly distributed in each object shown. Hint. Think about the given definition. B, C, E, D, T. What can we learn about the CM just from the previous activity? Looking at these shapes. Center of mass depends on the shape of the object. In some shapes, the CM point is outside the body of the object. The CM is the point around which the object spins in a uniform constant gravitational field. For a non-uniform field, because gravity varies across the body of the object, it spins around the center of gravity CD. We compare the difference between CM and CD. 0. Center of mass. M. Center of mass. For extended objects, the sum goes to an integral. dV. We break up the extended shape into that. Infinitesimal mass is the sum of. As shown. Center of gravity. Definition. Center of gravity. R sub CD equals numerator. Capital W sub 1. R sub 1 plus capital W sub 2. R sub 2 plus capital W sub 3. R sub 3. Note that. WWW. EN. WW. Are magnitudes of weight forces. In general. Center of gravity. Center of gravity CD. The CD is calculated similarly to CM. The only difference is the terms of the sums also with respect to the gravitational acceleration of each mass. Notice that when the gravitational acceleration GDI has the same value every mass location, this reduces the CM. All GDI cancels. This happens in a uniform gravitational field or in free space. CD only matters if there is a significant variation of gravitational field across the object. Because gravitational field varies very little closer to the surface of the Earth, we never need to worry about it. Use the CM instead, unless we're dealing with objects near black holes or other celestial objects. CD may matter when building skyscrapers. Three-dimensional center of gravity CD. Center of gravity of 2D in 1D objects. Introduction. Center of gravity of 2D in 1D body. Left figure. At an average shape plate in the xy plane. The location of the center of gravity. Right figure. The location of an infinitesimally small portion of the plate. Left figure. At an average shape wire in the xy plane. The location of the center of gravity. Right figure. The location of an infinitesimally small portion of the wire. Center of gravity wire. CD and CD are related. If the gravitational acceleration and density are constants, then we can derive CD from CD as follows. Replace them with the product of density and volume R. VV, where V equals part of A for some constant thickness, AA, and area, AA, dot, since R and AA are constants, they cancel from the equation. RRCC, CC equals R sub CM equals numerator, sum of height equals 1 n of m sub I, right point arrow, individual DD, where AA, E is the IDH area element n, AA equals, n area summation equals 1 n n, AA, E is the total area, T, and continuous form, mean average value, FR equals numerator, integral from A to B of x, dx and numerator, over denominator, E minus A, and denominator. Rectangle, FR equals numerator, sum of height equals 1 to EG for equal steps. Centroids and first moment various lines. Left figure, at an average shape plate in the xy plane. The location of the centroid of the area. Right figure, the location of an infinitesimally small portion of the plate. Centroid line. Left figure, at an average shape plate in the xy plane. The location of the centroid of the area. Right figure, the location of an infinitesimally small portion of the plate. X equals capital P sub y over cap A. Mean point of centroid. YY equals. Left figure, at an average shape line in the xy plane. The location of the centroid line. Right figure, the location of an infinitesimally small portion of the line. X XLL. Y represents axis here. First moment of the various lines. First moment of the various lines. Centroids of common shaped areas. Composite plates and areas. The location of the center of gravity of composite plate can be determined from the center of gravity 1, G2 open point plates. The location of the center of gravity of composite plate can be determined from the center of gravity 1, G2 open point plates. Composite area. Centroids of common shaped lines. Location of centroids of common shaped lines. R circular arc, semicircular arc, and arc circle. The x-axis is the dividing line between the triangle and rectangle. The y-axis is the left side of the rectangle. For the plane area shown, determine the first moment with respect to the x and y-axis and the location of the centroid. The x-axis is the dividing line between the triangle and rectangle. The y-axis is the left side of the rectangle. Strategy: divide the area into a triangle, rectangle, and semicircle with a circle cut out. Determine the centroid of each small area with respect to the axes. Find the total area and first moment of the triangle, rectangle, and semicircle. Subtract the area and first moment of the circle cut out. Compute the coordinates of the area centroid dividing the first moment of the area. Modeling: determine the dimensions of the centroids for each of the basic shapes, rectangle, triangle, semicircle, circle, dash. Find the total area and first moment of the triangle, rectangle, and semicircle. Subtract the area and first moment of the circle cut out. Analysis: compute the coordinates of the area centroid dividing the first moment of the area. Cap equals 54.8 millimeters. Rectangle. X equals 54.8 millimeters. Cap equals 36.6 millimeters. Rectangle. E equals 36.6 millimeters. Reflect and think. Given that the lower portion of the shape has more area to the left than the upper portion of the whole, the location of the centroid seems reasonable upon visual inspection. Centroid for volume CD. CD and CD are related. If the gravitational acceleration and density are constants, then we can derive CD from CD as follows. Replace them with the product of density and volume R. VV, dot, since R is constant, it cancels from this equation. RRCC, CC equals R sub CM equals numerator, sum of height equals 1 n of m sub I, R sub I, and summation and numerator over denominator, sum of height equals 1 n of m sub I, and denominator goes to numerator, integral of R dm and integral of numerator over denominator, integral of dm and denominator. Right point arrow, RRDD, integral DD, where VV, E is the IDH volume element n, V equals, n area summation equals 1 n n, VV, E is the total volume, V, centroid and first moment of volume, centroid and volumes of common 3D shapes, centroid of common shapes and volumes, centroid of common shapes and volumes, CD of composite bodies, CD of composite bodies. Locate the center of gravity of the steel machine element. The diameter of each hole is 1 centimeter. Sample problem 5.12. Where do we expect the center to be? By inspection, you should expect x and z to be considered less than 1/2 2.5 centimeters and 1/2 4.5 centimeters respectively, and y to be slightly less than -1/2 2 centimeters. Thus, as a rough visual check, these are the results we expect. 39. Strategy: form the machine element from rectangular parallel and the first cylinder and subtracting 2 centimeter diameter cylinders. Modeling. Analysis. Cap x equals 0.577 centimeters. Rectangle. X equals 0.577 centimeters. Cap y equals -0.955 centimeters. Rectangle. E equals -0.955 centimeters. Cap z equals 1.618 centimeters. Z equals 1.618 centimeters. Sample problem 5.12. Reflect and think. By inspection, you should expect x and z to be considered less than 1/2 2.5 centimeters and 1/2 4.5 centimeters respectively, and y to be slightly less than -1/2 centimeters. Thus, as a rough visual check, these are the results we expect. 43. Application of centroid. Loaded beams. Distributed loads on beams. A distributed load can be replaced with a concentrated load of magnitude equals the area under the load curve and line of action passing through the centroid load area. Assume the supported beam with roller point A and point B. A length 60 to support the distributed load is 1/5 and 3 point A increases linearly before 5 and 3 point B. A beam supports the distributed load is shown. Determine the equivalent concentrated load in reaction to supports. Assume the supported beam with roller point A and point B. A length 60 to support the distributed load is 1/5 and 3 point A increases linearly before 5 and 3 point B. Strategy: the magnitude of the concentrated load is equal to the total load of the area under the load curve. The line of action of the concentrated load passes through the centroid of the area under the load curve. Determine the support reaction by drawing the free body diagram for the beam and applying conditions of equilibrium. The area under the load is divided into triangles having a common side. Modeling analysis: the magnitude of the concentrated load is equal to the total load of the area under the load curve. F equals 18.0 kilonewtons. The line of action of the concentrated load passes through the centroid of the area under the curve. The area under the load is divided into triangles having a common side. X equals 3.5 meters. C vacuum approximately 1 mole approximately 1 local approximately 1 10 minus 50 minus 0.0 Determine the support reaction by applying equilibrium conditions. For example, successfully sum the moments about the two supports. By equals 10.5 kilonewtons. I equals 7.5 kilonewtons. Bx equals 0. And by some forces in the x direction. References: Vector mechanics for engineers statics dynamics. Publication 2019. Print NP. Let's look at this problem. We have this composite area, and we need to determine its centroid x bar and y bar. And because this composite area is symmetric about the y-axis, therefore the centroid location must be on the y-axis, and we know that the point that is on the y-axis, the x coordinate is 0. Therefore, in this case, we can x bar equals 0. All we need to do is to calculate y bar, which equals to summation y tutor a divided by summation a. So, what does this equation mean? We can tell that this composite area is made up by 4 component areas. So we have area 1 here, area 2 here, area 3, and lastly area 4. So, for each of them, we need to calculate their its area, and also we need to determine its own centroid y location y tutor. So, which means that for area number 1, its own centroid is here at the geometric center of the rectangle, and this much is the y tutor 1. So we need to determine y tutor for each of the component areas, and then do the calculation to determine y bar for the entire composite area. So for this problem, it's easier to set up a table because we have 4 component areas. So we have area number 1, 2, 3, 4 right here. And for the first column, we're going to calculate its individual areas with a linear square. So for area number 1 and 2, they're the same. So they have height of 100 millimeter with width of 20 millimeters, so that is 20 times 100 2,000 millimeter. Area number 3, we will have a length of 200 millimeter and a height of 20, so 200 times 20, that is 4,000 millimeter square. And for area number 4, the vertical one, we have height of 260 and width of 20, so 20 times 260, that is 5,200 millimeter square. So that's the first thing. And then for the next column, we're going to calculate y tutor location for each of these component areas. So for area 1, we know that from here to here, that is 260 plus 20 plus 20, that is 280. And from here to here, that is half of the height of area number 1, which is half of 100, which is 50. Therefore, y1 tutor equals to 280 minus 50. That is going to be, it should be from here to here, it's also 50. So 280 minus 50, so that's going to be 230, which is the same for area number 2, 230 here and 230 here. Area number 3 is going to be 280 minus half of its height, because its own centroid is here. So 280 minus half of 20, which is 10, 280 minus 10, 270. And lastly, for area number 4, its own centroid is here. So this is its y tutor location, y tutor coordinate, and that is 260 over 2, so 130. So that's the next column. For the next column, remember we need to calculate y tutor multiplied by a. As you know, we need to the third power, which is actually very important. So we're going to take these two numbers and calculate their product. So 2,000 times 230, so that's going to be 460, 000. Same thing, 460, 000. And then we have 1080, 000, 676, 000. So what's next is to add the first column and the third column together. So the first column, we're adding all the component areas together. The total area, that is 2,000 plus 2,000, etc. So that is 13200. And then we're going to add all these together as well. And that equals to 2676000 millimeter. Okay, so as you can tell, our y bar equals to the summation of y tutor a over the summation of a, which equals to this number 2676000 divided by this number 13200, and eventually that equals to 202.7 millimeter. Therefore, the central location of the composite area equals to 0, that is x bar, 202.7 millimeter. So we can try to mark it on our sketch. So 2.2, 202.7 is probably here. And that is the central location. In this video, we will focus on how to determine the centroid of an area, which is the geometric center of an area. From the previous video, we learned how to directly determine the location of the center of gravity for each body, which is the coordinate system, x bar, y bar, and z bar. And we also know that weight equals to mass times g, which is the gravitational acceleration, and for the general near-Earth station, it can be considered as a constant of about 9.1 meters per second squared. Therefore, the constant g can be cancelled out from the numerator into the denominator of this equation, and this new set of formulas now represent the coordinates of the center of mass for the body. In this case, the center of gravity is the same as the center of mass. And we also know that mass equals to density rho times the volume. And if we divide uniform density, then density rho can also be cancelled out from the numerator into the denominator of the equation. And now this new set of formulas represent the coordinates of the centroid of volume for this body. Note that centroid means the geometric center. And in this case, the center of gravity, the center of mass, and the centroid of the volume are all the same point. And if the volume has a uniform thickness, then we can further reduce the situation from 3D to 2 dimensional and cancel out the thickness from this equation. And now we have coordinates for the centroid of an area. And sometimes we can even further reduce the situation by cancelling out the constant width of an area and get coordinates for the centroid of a line. The line could be either straight or curved. Since the centroid is the geometric center of a volume or shape, if the volume or shape has any axis of symmetry, then the centroid must be on this axis of symmetry. Therefore, we can easily determine the centroid location of several common symmetrical shapes such as a cube, a circle, a rectangle, or a straight line. This can be used to help find the centroid for other unsymmetrical volume or shape. So let's look at this example, finding the centroid location for a triangle with base of b and height of h. Our demonstration is possible using two different approaches. First of all, we need to put this triangle into an xy coordinate system. So we can apply these two equations to find the centroid location. Since in these two equations x and y represent the coordinates of an point xy in this triangle, as defined in the differential element axis of location with sides of dx and dy. Therefore, the area of the differential element dA equals to dx times dy. Also, it is helpful to know the equation for this line, which is y equals to h over b times x, as we learned from the instructions probably in pre-calculus class. This is helpful because we will use this as the coordinates of the integration along the y direction. Therefore, first we calculate for x bar. The numerator is the integration of x times dA integrated along the y-axis from 0 to 9 h over bx and along the x-axis from 0 to b, and we get 1/3 hb squared. And we do the same thing with the denominator, which is 1/2 h times b. You might notice this is the way the area of the triangle 1/2 height times the base. That is correct. The denominator in this formula is simply the total area. Therefore, x bar is calculated to be 2/3 times b. And then we do the same thing for the y bar. The denominator is of course still the total area 1/2 h times b, but we need to integrate y dA, and eventually we get y bar equals to 1/3 h. This is the first approach. However, integration with two variables cancels times b together. Therefore, let's look at the second approach in which we only need to integrate with one variable. So we have the same rectangle with an xy coordinate system, but this time we choose the vertical strip with dx instead of the square to the volume differential element. The height of the strip is determined by the y coordinate of this point, which is h over b times x, as we determine the area from the equation of this line. Now, in these equations, as you can see, x and y are replaced by x tutor and y tutor. This is because now the differential element can no longer represent the particle. Therefore, in these two equations, x tutor and y tutor represent the coordinates of the central location of the differential element, which in this case is a rectangle, and we know that the centroid is right at the center. And we can tell that x tutor equals to x, and dA equals to the area of the rectangle, which is the height h over b times x times the width, which is dx. We plug these into the first equation. Therefore, x bar equals to 2/3 b, just like we got using the first approach. But here, as you can see, we only need to integrate one variable x. To find y bar, we do the same thing, but use the horizontal strip instead. And again, we get the same result. Y bar is 1/3 h. So it's up to you to decide what is the best method to use. As you can see, choosing the differential element converges to the calculation. Now we mark the centroid position on the triangle, and as you can see, it is located at 1/3 location to either side. Actually, if you recall, we used this conclusion before when replacing a linear distributed loading with one that shapes inside the triangle with a concentrated load. The centroid locations for common shapes have long been summarized and can be easily found online or in engineering textbook handbooks. For example, here is a screenshot of the Wikipedia page of centroids. You might find these information very useful.
Real life insurance really helps. Police are running things that are time to so these are like favorite things and about this one like something like that. Police are running things that everyone knows about. Somehow, police will be mechanical damage, but we don't really understand it. We don't know what to do, but the person knows about it, clever and reading the correct way, and just makes it work. That's like the smart person in everyone's city. So they start reading about police. I'm gonna slowly walk through how it works. Specifically, I want to introduce you to my favorite type of police. It's called snatch block. They're really fancy. They do tricks. Okay, let's start with blocks. You have to pick blocks, right? If you pick something up, you have to pick up all the weight of the thing, and when you're not, all the weight of you. How you good? You got part of that. The magic of a pulley is really the magic of a rope, because a rope is always in tension. You can't push a rope. If you pull on this side of the rope, that force transfers all the way through the pulley. So you basically can redirect force. That is the primary function of a pulley. Redirecting force. So you got it. The pulley changes the direction of your body weight. So you can use your own body weight to help pick something up. Very good. Is that hard? Not hard. Okay, so it's easier to pick up the pulley, but you can lean into it, right? So this is the part that starts confusing you. If you change the way the pulleys are arranged, you can make it easier to pick up stuff. You want the normal pulley or snap block? Snap block. There you go. Go for it. So you split it apart. Okay, you're out there. There you go. So this is the magic of snap block. You put the pulley in any place, anytime, as long as the rope, and snap block is on the rope. This is the part where you see it happening. Like, oh yeah, of course, you're with the pulley. But you don't stop to think. You're really understanding what's happening. So slowly pull. Is it really easy this time? It's a lot easier. Okay, so this is what's happening. The tension in the rope right here is being redirected by the pulley because the pulley is getting redirect force. But down here with the snap block, we're doing the same thing. We're redirecting the force. But you have tension in the rope and tension in the rope. So all you do is you put tension in the rope somewhere, and then you add up as many ropes as possible on the thing, and that's how you get mechanical damage. So in this case, how much force is on the snap block? You know, 2 times the tension. I don't know. I'm understanding things a lot better. I can work with it in my hands. So I reframe the pulleys and snap blocks. I'm gonna read these things up and generate a model of how we can put the cinder blocks. So when I pull on this rope, that tension transmits itself all the way through the rope to the very end. Wherever the rope is, there's also tension. If I pull here, think about the word pulley. It pulls on the rope on the other side. The pulley right there. That pulls on the rope there at the bottom, which then pulls on the rope on the other side of that pulley, which ultimately pulls against that hook at the very end. All the ropes are in tension. Now, if you look down there at the center block, you'll notice that there are 2 arrows pulling up on that pulley. That's why we get twice the force on the center blocks. So we're gonna pull harder. Can we just add more ropes in tension? Yes, we can. Using this. It's basically a double pulley. So we call this a block and tackle. Instead of ropes pulling underneath force, just a little bit of force here. You're not thinking here. It's like 10 pounds of force. I just barely pulling it all. This is the same number of ropes and my pulleys and everything. Just find out what you want. So I have a scale. I'm gonna attach a scale to the input of the rope. And remember, if you put tension all the way through. So as I pull here, I have 1, 2, 3, 4 ropes connected to the thing we're pulling. So I have 2 pounds here. Look at that. I get 8 pounds on the output. That's awesome. I'm getting 4 times the force, but I'm only getting 1/4 as far. How do you think we can go this? See, we can go again. So now I have 2 blocks with 4 pulleys each, which count up 1, 2, 3, 4, 5, 6, 8. We have 8 ropes in tension on that block. So as I pull here, look at this. That's nuts. That is a little bit of force and a lot of output. That is some serious mechanical damage. Okay, so the ropes are supposed to be a lot. The ones over here are this much. Let's break this apart again. Oh man, that's a great shot. Okay, so we got one pulley. Let's count the tension again. 1, 2, 3, 4, 5, 6, 7, 8. I put 2 pounds here on the input. That's a lot of force on the output. So you're not like the ropes are moving at a rate. So think about this. On this side over here, that rope is tied up there. It's not going to move. On this side, I'm pulling the rope. It has to move as much as I pull it. And the same for this one. Just redirecting strain. After that, everything is affected by how much this moves. So just playing around with here, you can see that these ropes move a whole lot more than how they're at all. There's a lot going on here. Now this is something that yes, you probably explain the words, but if you have a fundamental understanding of how this works, and you know how to use it to your advantage, you can use yourself as some really interesting situations. For example, you have a drive shaft rope. How to get a truck. I'm going to fly the trailer without a winch. Snap block. We're going to pull systems. So we pull this entire truck on the trailer using only ratchet straps. So figure out what the training force resistance is forever. That's a nice guy named Jeff. Drop up, instantly understood our pull system. Anyone can do this truck. We just take one ratchet, but Jeff's truck is placed. Pull the truck, pull the trailer. What is 91 Jeff's truck? People think it's going to go for more. For example, Jeff got all the hands. What's that snap block? Oh, sorry, snap block. That's great. I'm going to put that. Yeah, go. I'm going to Jeff's guy on the micro block. Watch this snap block. Starts working. He knows what to do. Also, his hands are just amazing. Watch his hand work. Snap block engage. Snap what you got. Dude, I'm trying to. Yeah, triple. Oh, dude, that's a big my friend. Any day you use snap block is a good day. So yeah, snap block is a very situation. No one uses it to make friends. And they also be a ton of fun. This one's basically just snap blocks. You have the ability to break apart a pulley. You can insert a cable into it without having to disconnect it from your end. This is the definition of a snap block. Pulley where you can insert a line without having to take part of the line where it's up to. Snap blocks are amazing. We're also going to get amazing use of reinforcement like this. That's snap block. That's awesome. Okay, so get the video about snap block. Let's get a G stuff. Let's do that. Let's take a G stuff. You might get to find your tree. Pull the winch out. Pull the cable directly to that tree. We're going to go. Where's snap block? Snap block. Right, right. Oh, that's scary. It's a lot of force, dude. That's good. That's a lot of force, man. Awesome. Well, this has the same mechanical damage, but it does it way. Here we add up the tension on these ropes. We have 1 + 1 = 2. If we have 2 + 2 = 4, and 4 + 4 = 8. We can come up with 8 to 1 mechanical damage just like that with less pulleys. This is fascinating. One of the 3 problems constantly designing Archimedes. So one of Archimedes, I'm library handbook by a man named Plutarch, who mentions the interaction between Archimedes and King Hero of Syracuse. It's a really interesting story, but something better if I tell you this final word. So look at this. Archimedes writes a letter to King Hero of Syracuse. He's like, yo, King Hero, I'm really good with pulleys and stuff. And Hero's like, what's great? Archimedes is like, well, Bill, if you need worship. And Hero's like, yo, dog, here's your worship. And Archimedes is like, yo, dog, I hear you like pulleys. I got pulleys. And Archimedes does something amazing. Under his own physical strength, he pulls his entire worship out of the dock, which totally impresses the king, because that's what happens when you know how to use pulleys. You impress people. So people have been using pulleys and snatch blocks for thousands of years. It impresses all the Archimedes. They're going to use it for thousands more. That's why you need to know how to use a snatch block. Don't take my word for it, though. I'll let their astronaut Chris have Bill explain everything to you. The difference between being on Earth and being space is that you're weightless. And when you're floating on weightless, like on space shuttle, it's not really leverage. You can't dig your feet in, you can't use the weight of your shoulder in place. So the only way to hook up the land and hook on the other end
and apply a steadily increasing force is really important. And that's why on board the station we have snatch blocks. They're part of the equipment. In fact, there's a special storage block for them that contains a couple, and they get used regularly, both inside the ship and outside the space dock.
You're a problem. Hello, you pick up. We use snatch blocks. Snatch blocks are amazing. I think something else is amazing. That is the sponsor for this video.
Test your questions. Friday the 28th of August 2020. 1. 11:01 a.m. Machine. I think hydraulic system raising arm. Calculate the forces on the base of the machine A and B. 2. 3. Centroids. The ZG wires down some pin. The diagonal length is 40 centimeters and horizontal vertical length is 20 centimeters. What is the value of x force to y balance? Centroids. Calculate the first moment of area and centroid of the following shape. 4. Friction. It takes 20 and to grab another base of the center. What force is required to achieve this? The screw is a single thread 1 centimeter radius and 3 millimeters pitch. Mu equals 0.3. 5. Internal force. Determine the internal reaction today. There's a row support beam between 0. 6. Calculate the minimum force required to remove block B. 7. A. A 1 millimeter radius single thread screw with 1 millimeter used to hang 10 kg mass. For 1 minimum static friction coefficient, the screw self-locking. B. Using your answer part A. For mass of 20 kilograms. What is the moment required to screw in the screw? Moment of inertia. WMEC WCID 101.7 lesson 1. Copyright. Lesson. In this lesson you will recap first moment of area and rotational inertia. Understand why the second moment of area represents distance floating into uniform mass distribution. Understand how to calculate second moment of area. Recap. First moment of area and centroid is often calculated for x and y coordinates separately. E.g. y, x, y, y equals a, e, y, y, e, enters a, e, equal, enters a, e, y, e, y, y, a, integral, d, quadruple a equals q. Recap. Rotational inertia. Rotational inertia represents the quantity that tells us how hard it is to rotate ice heat up, slow down, and altitude around a given axis. Example of the second moment. SS. Is less than SS. Recall from rotational K that is the rotational inertia of the small mass m. Recap. Rotational inertia. The rotational inertia for distributed set small masses is given by based on the sum principle. 2. Center of mass cm rotational inertia. Object radius rotate around the cm axis with the mass distribution close to the axis of rotation in a given plane. Recap. Rotational inertia. Kappa equals kappa sub cm plus kappa d squared. Rectangle. If we want to rotate around a different axis which is parallel to the center of mass axis, then as the distributed farther from the axis of rotation, the object becomes harder to rotate. Recall. We use the parallel axis theorem to calculate this new rotational inertia as follows. Cm axis. Parallel axis theorem. Center of mass rotational inertia. X. Measure area distribution. Centroid. As far as the axis goes to the centroid, the second moment area gives a good indication about the stability of moving and floating. Here in the x direction for homogeneous materials. Uniform density. Rotational inertia and second moment area. 2 equals ICCC plus MDD2. ICCC equals AR. RR2. AA. Second moment from the center of area axis. Center of mass rotational inertia. Kappa sub A equals kappa sub CA plus kappa d squared. Rectangle. Parallel axis theorem. For second moment area. CMCA. Axis. Bending moment and area distribution. Bending moment is explained intuitively. Zero mathematics video. Second moment area. Penultimate derivation. Distribution of material and internal forces. Second moment area. Beam cross sections. Diagram. Engineering drawing. Description automatically generated. Diagram. Engineering drawing. Description automatically generated. Common shapes. Rectangular shaped shaded area in the first quadrant with base P, height h, and centroid point C which is located at the intersection of the x and y axis. Triangular shaped shaded area with base P, height h, and centroid point C which is located on the x axis. Circular shaped shaded area. Center of the origin with radius r and centroid point O. Semicircular shaped shaded area in the first and second quadrants. Symmetric by the y axis. Center of the origin with radius r and centroid point C. Quarter circle shaped shaded area in the first quadrant with radius r and centroid point C. Parallel axis theorem. As expected, the parallel axis. Theorem is used for second. Moment of area. Other dimensions to know. The generic shape figures position in the xy plane. The area that is positioned in the first quadrant with coordinates x, y. The area that is located distance r from the origin. The polar moment of inertia is important parameter in problems involving linear shafts and rotations of slabs. The polar moment of inertia is related to rectangular moment of inertia. The polar second moment of area is used to describe resistance to torsion. Y. Hint. Notice that we are integrating area in all directions around a point on the plane height perpendicular axis of interest. Moment of inertia. 172.24191.17 underscore volume 4 OEDL 4 graphic PowerPoint MHN underscore DCM MHN underscore DCM text project MHN 37 final file Java 98 underscore label underscore find moment of inertia of the school district line candidate. Moment of inertia. IIDD equals IIDD plus AI 2 equals kappa sub superspace kappa kappa IA moment of inertia. Step 1. Determine moment of inertia for area 1. Step 2. Determine moment of inertia for area 2. Step 3. Find the total moment of inertia of the x axis. Step 4. Repeat the same steps to find total moment of the y axis. Y. AA1. 20. 60. 40. 20. Moment of inertia. 1. We need to find the centroid to be able to find the moment of inertia. 2. To find the moment of inertia of an object of the x axis. Moment of inertia. From previous lecture slide by using the reference point indicated in the figure. AA1. 60. 20. 20. Y. X. 20. 70. 20. 30. 20. 46. Moment of inertia. AA1. 20. 40. 20. 20. 20. 46. Y. X. Moment of inertia. Fill in the blanks. Y. Centroid components. Mod components. Parts. AA. XX. YY. IIXX. IIYY. DDXX. DDYY. ADDXX 22. AID 22. IIXX plus AID 22. IIYY plus ADDXX 22. Rect. Circle. Total. Moment of inertia. Fill in the blanks. Y. Centroid components. Mod components. Parts. AA. XX. YY. IIXX. IIYY. DDXX. DDYY. AID 22. IIYY plus ADDXX 22. Rect. 15,000. 50. 75. 2.8125 times 10 to the 7. 1.25 times 10 to the 7. 0. 0. 0. 0. 2.8125. 1.25 times 10 to the 7. Circle. 1,960. 50. Moment of inertia. Calculate the following object. Like a centroid. Equal moment of inertia about the centroidal axis. Equal moment of inertia about the centroidal axis. 20. 20. 60. 60. Moment of inertia. Parts. AA. XX. YY. IIXX. DDXX. DDYY. 1.5 times 10 to the parts. AA. XX. YY. AXX. AYY. Rec 1. 1.10. Rec 1. 10. Total. 2,800. 76,000. 76,000. XX 20. 20. 60. 60. 1. 2. Moment of inertia. Calculate the following object. Like a centroid. Equal moment of inertia about the centroidal axis. Equal moment of inertia about the centroidal axis. Moment of inertia. Parts. AA. XX. YY. DDAA. Rec 1. 10. 40. Rec 1. 10. 4. Rec 1. 4. 6. 2 parts. AA. XX. YY. AA. Rec 1. 1.10. 64,000. Rec 2. 1,210. 6. Rec 1,200. 74 total. 1. XX equals 34. Y. 1. 2. Y. Normalize. Second moment of area. Other dimensions to know. The generic shape figures position in the xy plane of area A. Rectangular strip parallel to the x axis. Traveling the y axis. Replacing area that has moment of inertia with equivalent strip that has the same moment of inertia. The generic shape figures position in the xy plane of area A. Rectangular strip parallel to the x axis. Traveling the y. In this problem, we have a 82 gram crate that is simply standing on this moving cart on this inclined surface with a 15 degree angle horizon. And because the crate simply stands on the cart, it means that there's nothing else that keeps this crate from moving except for the frictional force between the surface of the crate and the cart. So we need to determine this acceleration, the maximum acceleration that the cart can have without causing the crate to move. We could either tip over or slide relative to the cart. This is the same as asking what is the minimum acceleration they needed for the crate to start moving. We need to determine when that happens, when the motion happens, the relative motion of the crate with respect to the cart. Is the crate sliding relative to the cart or is it tipping over? The static friction coefficient is given between the crate and the cart. So let's use this example to illustrate typically how we deal with this kind of problem. This is by way of translation problem. There's no rotation or motion involved. So we start with drawing a free body diagram of the crate. So the gravitational center is given the dimension of the crate is given as well. It is subject to the weight, which is mg, and also the normal force from the cart. Right now we do not know exactly where the location of the normal force is. And because the cart moves up, therefore the relative impending motion of the crate with respect to the cart is down. So this is the direction of the relative motion of the cart. Therefore frictional force develops to prevent impending motion. Therefore frictional force is up as well. So we need to determine the direction of the frictional force that will quickly help with the analysis. We can tell that the frictional force is actually the only force that makes the crate to move up with the cart. If the frictional force is in the other direction, the crate will no doubt slide down. So now we have completed the diagram. Let's draw choose a coordinate system that's align our x and y coordinate system with inclined surface and then perpendicular to it for convenience. And also we draw the kinetic diagram, which is basically drawing the MEG, which is in this direction along the inclined surface. This is the mass center on the gravitational center of the crate. So with this now we can start writing our equations of motion. So let's write the first equation starting with force along the y direction, which is again in this direction. And that equals to the normal force minus w times cosine 15 degree equals to 0. And this is n minus mg, which is 80 times 9.81 times cosine 15 degree equals to 0. Also, resultant force along the x direction, x is in this direction, equals to frictional force minus w sine 15 degree, which equals to frictional force minus 80 times 9.81 times sine 15 degree equals to mag, which is 80 times ag. So now here we have two equations, equation 1 and equation 2. Now we have normal force, frictional force, and ag. So we have three unknowns, only two equations, obviously not enough to solve for all of our unknowns. You know, we have to solve for normal force here. So from the first equation we can find out that normal force is equals to 758.1 newton. So now in order to solve for the other two unknowns, we need one additional equation. So we get that. We can write different third equation based on the assumption we make. So if we make the assumption that let's assume first sliding occurs. This is when the crate slides relative to the cart, so the crate will slide down in this direction. If that happens, we will know that the frictional force between the crate and the cart has now reached the maximum static friction, which now can be evaluated by this equation mu s times 10. You cannot use this equation unless you know that the static friction has reached the maximum value. This is when sliding is about to occur. So mu s is given as 0.5 times normal force, which is solved earlier, 758.1. So this is our third equation. So from here we can solve for frictional force to be 479 newton. That's actually not important because it's ag that we need. Ag can then be solved from the static equation by substituting frictional force into it, and ag equals to, in this case, 2.20 meter per second squared. This is not the final answer. This is the acceleration needed for sliding to occur. However, what if it's tipping over that occurs first? If that's the case, then frictional force no longer equals mu s 10. Remember, this equation can only be used when frictional force reaches the initial value when sliding is about to occur. So in this case, we cannot write this third equation. We need another third equation. Based on what we learned back in statics, we know that when tipping over is about to occur, we actually know the location of normal force. Before we know the location of normal force, but now we know that the normal force location has to be placed at this corner, point A. So with this specified location, now we can write our moment equation of motion. So if we start with the moment about point G, which is gravitational center, because we have translation, therefore the result moment about point G equals 0. This is only true at point G. If we start with the moment about other points, the result is not 0. So this is only true for translation for moment about G gravitational center. So in this case, if again we assume counterclockwise to be positive, then the frictional force is causing counterclockwise rotation with moment arm 1.5 meter, and the normal force is causing clockwise rotation with moment arm 0.5 meter. And that equals 0. And because we know what normal force is, now we can solve for normal. Sorry. So let me see that first. This is our third equation now. So now with 1, 2, and 3 equations, we can solve for frictional force to be 252.7 newton. Similarly, substituting into the second equation, we can solve for ag to be 0.60 meter, 62 meter per second squared. So again, this is the maximum acceleration the car can have without causing the crate to tip over. Before I further analyze the situations, let me say that I can actually write an alternative moment equation. We can start with the moment about point A. This is not 0. However, the result moment about point A, which equals to the moment cosine of weight. If we take counterclockwise to be positive, then this equals to w times sine 15 degree times 1.5 minus w times cosine 15 degree times 0.5. So that's the y-axis component, and that's the y component causing moment about point A. Normal force and frictional force pass through point A, not moment about point A, and this equals to not 0, but the kinetic moment mk about point A, which equals to the moment caused by the kinetic force mg about point A. mg is causing clockwise rotation about point A, therefore this equals to negative m times ag times the moment arm of 1.5, because ag is placed at the rotational center. Therefore, from this equation alone, actually, we can solve for ag, which will give you the same answer. So this is the alternative method. Either way, now we have evaluated two accelerations. One is the acceleration that will cause sliding to occur. The other is the acceleration that will cause tipping over to occur. And if we compare them, we realize that the second situation only takes a smaller acceleration. Therefore, the final answer should be ag equals to 0.62 meter per second squared, and this is when tipping over occurs. Because it takes smaller acceleration to cause tipping over. It is easier to cause tipping over. It is harder to cause sliding relative sliding. So that's the final answer to this problem. So enough, you have made assumptions, done calculations, so you have to make a decision. In this problem,
Kinematics of particles. WMEC 1001. Week 7. Introduction. Kinematics. Study of the geometry of motion. Relates to displacement, velocity, acceleration, and time without reference to the motion. Kinetics. Study of the relation distinct between forces acting on the body, the mass of the body, and the motion of the body. Kinetics is used to predict motion caused by given forces that determine forces required to produce motion. Race force acting on it. Drag force, aerodynamic downforce, and drag. Kinematics. Kinematic relationships are used to determine the trajectory of snowboarding, cleaning jump, the orbital speed of a satellite, and acceleration during a direct line. Introduction. Rectilinear motion. Position, velocity, and acceleration of particles moves along a straight line. Curvilinear motion. Position, velocity, and acceleration of particles moves along a curved line in 2 or 3 dimensions. Curvilinear motion. Zero limb. The velocity vector stands to the path proportional to the change in the position vector, i.e. proportional to displacement. VV increment r. Curvilinear motion. Rectangular components of velocity and acceleration 1. Velocity vector. Acceleration vector. Graphical solutions 1. No. Acceleration data from head vectoring around the boxing. Graphical solutions 2. Given the VT curve. The AT curve is equal to the VT curve slope. Graphical solution 3. Given the VT curve. The change in position between T1 and T2 is equal to the area under VT curve between T1 and T2. Rectilinear motion. Position, velocity, and acceleration 3. From the definition of the derivative. Concept quiz 1. A, the velocity of a particle is always positive. B, the velocity of a particle is equal to the slope of the position time graph. C, the position of a particle is 0. Then the velocity must 0. D, the velocity of a particle is 0. Then its acceleration must be 0. Concept quiz 1. A, the velocity of a particle is always positive. B, the velocity of a particle is equal to the slope of the position time graph. C, the position of a particle is 0. Then the velocity must 0. D, the velocity of a particle is 0. Then its acceleration must be 0. Rectilinear motion. Position, velocity, and acceleration. VV equals. V equals the x over dt equals 12 minus 3t squared. What are x, p, and at t equals 2? At t equals 2s, x equals 16 meters, b equals v max equals 12 meters per second, a equals 0. Dash. Note that the max equals 1 equals 0, and the slope of the velocity curve is 0 at this point. What are x, p, and at t equals 4s? At t equals 4s, x equals x max equals 32 meters, b equals 0, a equals minus 12. Sample problem. Determine. Velocity and elevation above ground at time t. Highest elevation reached by ball in corresponding time, and time when ball hit the ground and corresponding velocity. Strategy. Acceleration is constant, so we can directly integrate by defining dt and yt. Solve for t when velocity equals 0, time for maximum elevation, and evaluate corresponding altitude. Solve for t when altitude equals 0, time for ground impact, and evaluate corresponding velocity. Sample problem. Integrate by defining dt and yt. V of t equals 10, m over s minus 9.81, m over s squared. V of t equals 10 seconds minus 9.81 seconds dt. Y of t equals 20 meters plus 10, m over s close to t minus 4.905, m over s squared close to t squared. Rectangle. Y of t equals 20 meters plus 1 ct minus 4.905 milliseconds dt2. Sample problem. Define the highest elevation reached. First solve for t when velocity equals 0. T equals 1.019 s. Rectangle. T equals 1.019 s. Y equals 25.1 meters. Rectangle. Y equals 25.1 meters. Sample problem. Define the velocity when the ball hits the ground. First solve for t when altitude equals 0, and then evaluate the velocity at that time. T equals minus 1.243 s over meaningless. Close to t equals 3.28 s. Rectangle. T equals minus 1.243 s meaningless. T equals 3.28 s. V equals minus 22.2 m over s. Rectangle. V equals minus 22.2 milliseconds. Rectangular components of velocity and acceleration predict motion. With initial conditions. Integrating by fields. Motion in horizontal direction is uniform. Motion in vertical direction is uniformly accelerated. Motion in vertical gear placed by two independent rectilinear motions. X, Y. Sample problem 1. Sample problem 2. Given. Open bracket. Close parenthesis y equals minus 9.81 meters per second squared. Open bracket. Close parenthesis x equals 0 meters per second squared. Vertical motion. Uniformly accelerated. Vy equals. V sub y equals open parenthesis y. Close parenthesis 0 plus versus y equals 9 minus 9.81 t. Open parenthesis 1. Close parenthesis y equals open parenthesis y. Close parenthesis 0. T plus 1 half that squared. Y equals 19 minus 4.90 t squared. Open parenthesis 2. Close parenthesis y squared equals open parenthesis y. Close parenthesis 0 squared plus y versus y squared equals 8,100 minus 19.62 y. Open parenthesis 3. Close parenthesis. 1 y equals y 0 t plus 1 2 y equals 90 t minus 4.90 t2. 2 y 2 equals y 2 plus y 2 equals 8,100 minus 19.62 y 3. X, Y. Sample problem 2. Horizontal motion. Uniformly accelerated. Choose positive x right shown. X equals open parenthesis sub x. Close parenthesis sub 0 to t and subscript x equals 155.90. Sample problem 3. Horizontal distance. Predictable strikes the ground at y equals minus 150 meters. Substitute into equation 1 above. Solve for t. We take the positive root. Dt equals 19.91 s. Substitute t into equation 4. X equals 3,100 millimeters. 0 equals 8,100 minus 19.62 y. Maximum elevation above the ground equals 150 meters plus 450 meters equals 563 meters. Launch of 180 meters per second at an angle of 30 degrees from horizontal. Initial velocity is 150 meters above bottom surface. Acceleration is 9.81 meters per square second due to gravity. Sample problem 4. Because there's no air resistance, you can keep the vertical and horizontal motion separately and intermediate right down the rate equation of motion. If you do want to include air resistance, you must know the acceleration function speed. You'll see how to derive this integral, and then you use the basic dynamic relationships, separate variables, and integrate. Concept quiz 5. If you fire a particle from 150 meters above the ground, cx problem 1.1.0, one angle will be the radius horizontal distance x. A launch angle 45. B launch angle less than 45. C launch angle greater than 45. D depends on the launch velocity. Concept quiz 5. If you fire a particle from 150 meters above the ground, cx problem 1.10, one angle will be the radius horizontal distance x. A launch angle 45. B launch angle less than 45. C launch angle greater than 45. D depends on the launch velocity. Motion of several objects. Motion of several particles. Motion of several particles. Dependent motion. Block A is attached to a rope that goes up stationary pulley CD. Goes down moving pulley after it's attached to block B, and then goes back to be affixed to the ceiling G. The position of each block is distance from the ceiling. Motion of several particles. Dependent motion. A rope comes down from the ceiling, passes through a moving pulley attached to block A. It then goes up past a rope fixed pulley to the ceiling, then down to a moving pulley attached to block B, then up to a fixed pulley to the ceiling, and finally down into block C. Sample problem 4. Group problem solving 8. Block lies on horizontal surface, while block B moves up and down. A rope on the right side passes over a stationary pulley, passes through a pulley attached to block B, up to a stationary pulley, and back down to the attached to B again. Strategy. Sketch a system and choose coordinate system. Write out constraint equation. Differentiate constraint equation to get velocity. Group problem solving 9. Sketch a system and choose coordinates. X underscore A is the horizontal distance from the first fixed pulley block B, y underscore B is the vertical distance from the same pulley block B. Differentiate constraint equation to get velocity. X underscore A is the horizontal distance from the first fixed pulley block B, y underscore B is the vertical distance from the same pulley block B. Group problem solving 10. Block lies on horizontal surface, while block B moves up and down. A rope on the right side passes over a stationary pulley, passes through a pulley attached to block B, up to a stationary pulley, and back down to the attached to B again. Reflecting thing. Block lies on horizontal surface, while block B moves up and down. A rope on the right side passes over a stationary pulley, passes through a pulley attached to block B, up to a stationary pulley, and back down to the attached to B again. References. Vector mechanics for engineers, statics dynamics, television, 2019. Ferdinand P. Peter E. Russell Johnson Jr. David F. Mazurek, Philip J. Cornell, Brian P. Self, McGrath. Relative motion. WMEC 101. Copyright same. Motion relative to frame translation 1. Motion relative to frame translation 2. Motion of several particles. Relative motion. XFTD equals x alpha plus xFTDA. ABDA equals ABD minus particle equals. Relative acceleration of b with respect to a. Sample problem 1. Sample problem 1. Sample problem 2. Ball number from initial height 12 meters, initial velocity 18 meters per second, constant downward acceleration 9.81 meters per second due to gravity. Modeling analysis. Sample problem 2. Modeling analysis. Open elevator starting from initial height 5 meters, moving upward at constant velocity of 2 meters per second. Sample problem 3. When the ball is the elevator, their position is equal. T equals minus 0.39 s over meaningless. Close rent equals 3.65 s. Rectangle. I equals minus 0.39 s meaningless equals 3.65 s. Substitute impact time into equation for position of elevator and relative velocity of ball with respect to elevator. When the ball is the elevator, their positions are equal. YYE equals 12.3 meters. V sub calculated by Capian sub equals minus 19.81 MOS. Rectangle. VVD equals minus 19.81 milliseconds. Sample problem 4. Reflecting thing. Concept quiz 3. Train A is going westward at 66 km per hour. Train B is going 48 km per hour. 25 degrees north east. A. Train A is going westward at 66 km per hour. Train B is going 48 km per hour. 25 degrees north east. B. 25 degrees north east. C. 25 degrees southwest. D. Less than 25 degrees southwest. Concept quiz 3. Train A is going westward at 66 km per hour. Train B is going 48 km per hour. 25 degrees north east. A. Train A is going westward at 66 km per hour. Train B is going 48 km per hour. 25 degrees north east. B. 25 degrees north east. C. 25 degrees southwest. D. Less than 25 degrees southwest. West. Sample problem 1. Determine the position, speed, and acceleration of car at t equals 5 s. Determine the position, speed, and acceleration of car at t equals 5 s. Using vectors equation 11.30, 11.32, and 11.33 or graphical approach, determine relative position, velocity, and acceleration. Sample problem 2. Define axes along the road. Given. Determine motion of automobile A. We have uniform motion for so. At t equals 5 s. Triple A equals 0, B A equals 10 kk, S right point near, R A equals 50 kk right point near. Sample problem 3. Determine motion of automobile B. We have uniform acceleration for so. At t equals 5 s. Ab equals 1.2 kk, S2 down point near, BD equals 6 kk, S down point near, RBD equals 20 kk down point near. Sample problem 4. Ab equals 1.2 kk, S2 down point near, BD equals 6 kk, S down point near, RBD equals 20 kk down point near. Right triangle with horizontal position of being on side 50 meters, vertical position of being left side 20 meters, and relative position of being with respect to being hypotenuse. I equals 21.8 operator. Right triangle with horizontal velocity of being top side 10 meters per second, vertical velocity of being left side minus 60 meters per second, and relative velocity of being with respect to being hypotenuse. BD equals 31.0 operator. Relative acceleration of b with respect to a is just the same acceleration of b minus 1.2 meters per second. Or you can solve the problem using vectors to obtain equivalent results. Physically, a rider in car A would see car B traveling south and west. Sample problem 5. References. Vector mechanics for engineers, statics dynamics.
This lecture covers the analysis of static determinant trusses using the method of sections. Please review the previous lecture before continuing with the points. Consider the static determinant truss. Suppose we want to calculate force in number CD only, without analyzing the entire structure. We can do this by cutting through a few truss numbers in order to split the structure into two parts. When we cut a truss number, we expose the internal force. In this case, since we cut through 3 numbers, we expose 3 number forces. We know that when a truss is in state equilibrium, the equilibrium equations are satisfied for the entire structure, and for any isolated part of it. So in this case, we can argue that since the entire truss is in state equilibrium, these two parts must also be in equilibrium. That is, the 3 equilibrium equations must be satisfied for each part. To compute the force in number CD, we only need to consider one of the diagrams. We don't need both of them to do the calculations. Let's consider this diagram, for which we can write 3 equations in terms of FCD, FCH, and FTH. The equations are: the sum of the forces in the x direction must be 0. The sum of the forces in the y direction must be 0. The sum of the moments, say, at point H, must be 0. We can solve these equations for the unknown number of forces. If we want to calculate FCD only, we can use the third equation. It gives FCD equals negative 36k. If necessary, we can use the other equations to determine the other unknown forces. The second equation gives FCH equals negative 50.9k. Then we can use the first equation to get FCH. Note for this particular problem, we do not need to know the support reactions in order to determine the force in number CD. But in some other cases, we may have to calculate the support reactions before we apply the method of section to solve the problem. For example, suppose we want to calculate the tension force in number BC. We calculate numbers FC, FC, and BC, dividing the truss into two parts. This leads to a total of 5 unknown forces for the left diagram. There are 3 unknown forces and 2 unknown support reactions. On the right diagram, it's having a total of 4 unknowns. But we can only write 3 equilibrium equations for each part. So we end up with more unknowns than equations, which means we cannot solve the equations for the unknowns. Therefore, it is good practice to calculate the support reactions before splitting the truss into two parts. We can calculate support reactions by writing the static equilibrium equations for the entire truss. The sum of the forces in the x direction must be 0. The sum of the forces in the y direction must be 0. The sum of the moments about point A must be 0. Solving these equations for the unknowns we get. Knowing the support reactions, we are now ready to apply the method of sections for determining the force in number BC. We cut the truss like this. Now we can use the equilibrium equations to calculate the unknown number of forces. Since we are interested in determining FBC only, we can calculate that force by writing the moment equilibrium equation at point F. Solving this equation for FBC, we get FBC equals negative 36k. Let's summarize what we've learned so far. The method of sections is suitable for calculating a few number forces without needing to analyze the entire truss. 4 main steps are involved using this method. 1. We calculate the support reaction for the truss. 2. We cut the truss through the target number and the other numbers in order to divide the structure into two separate parts. This exposes the internal forces in the cut numbers, hence one force per cut number is exposed. 3. We draw the 3 body diagram for one part, showing the support reactions and the exposed number forces, and relevant distances and angles on the diagram. 4. We write and solve the equilibrium equations for the 3 body diagram in order to determine the unknown forces. Let's apply the procedure to solve the problem. Consider this static determinant truss. Suppose we wish to calculate the force in number EF. We start by calculating the support reactions for the entire truss. Here's the 3 body diagram of the system for which we can write 3 equilibrium equations. Solving these equations for the unknowns, we get the values for By, Ay, and Ax. Let's cut the truss horizontally like this. The cut divides the truss into two separate parts, exposing 3 number forces, one of which is a target force. We can use either of these diagrams to calculate the target force. Let's take the lower 3 body diagram. Note the angle that FEF makes with the horizontal axis. We calculate the angle alpha. We need to know the angle in order to calculate the unknowns. We can determine alpha using simple trigonometry. Tangent of alpha equals 2 over 5. Hence alpha equals 21.8 degrees. To determine FEF, we can set the sum of the forces in the x direction to 0. Solving this equation for the unknown force we get. In summary, using the method of sections, we can calculate the force in a number without needing to analyze the entire truss. For most static determinant trusses, we can easily apply the method of sections to calculate number forces. However, there are a few cases that you need to be aware of when dealing with this method. Case 1. Calculate K truss for calculating number force. Case 2. What if the number of unknowns is more than the number of equations? Case 3. When using the method of sections,